In today's lecture, we're going to be discussing data structures and specifically data structures in an assembly context. Now, in this lecture, we will not learn any new assembler per se. However, we will rather utilize the knowledge we already have in assembly to try and realize very common data structures. Now, one obvious downside to using assembler to implement a data structure is that generality is likely going to be lost. Specifically in a high-level language like C++ or Java, I would be able to templatize a container. For example, in C++, I have the tree, the object in the STL, where I can templatize what I want my nodes to actually contain. For example, it could be a tree where each node simply stores an integer or even a custom type or a double. There's a lot of options available to me, and I only have to implement the tree once. Now, in an assembler context, obviously we don't have that level of templatization at all available to us, so we have to make that kind of compromise. However, given assembler's low-level nature, we can utilize the specific detail about the intended type that we wish to store in our objects to our advantage, namely in terms of speed and also in terms of size. Size is quite obvious because we can control certain padding constraints and things like that that we might not have explicit control of in a higher level language. Now, it should be mentioned that one could try and write an in-between layer between a variant of assembler through something that you write yourself that induces some kind of templatization, and things like that have been done in the past. However, it is well beyond the scope of this course, but it is an interesting thing to give a look up if you're curious. But for the moment, I think if you want to construct an entirely generalized container, your best bet it would be to use a higher level language. But if you're trying to eke out some performance in a specific situation, then assembler might be the tool of choice. Now, the data structures that we'll be focusing on in this course are linked lists, double linked lists, hash tables, binary trees, and the obvious extension will be the k-array trees. And in the practical / assignment component of I'm not going to spend too much time discussing how these data structures work. If you feel a little bit rusty, it might be to your advantage to quickly stop this video and do a read up on how linked lists work, for example. I think the material itself will be somewhat self-explanatory even if you are a bit rusty, but I just want to preface I'm not going to waste much time discussing the actual algorithm itself. This is really a lecture on how to implement these data structures in an assembler context as opposed to a data structures lecture. So with that in mind, we're now going to discuss linked lists. Now, if we were to implement a linked list, there are a number of ways we could try and go about it. The method we are going to use in this case is in accordance with the one used in the book, and it's probably the simplest one to implement. It might be a little bit more challenging for a user to work with it, however, but that's it. This is more just to illustrate how to build a linked list in an assembler context. Now, a linked list, generally speaking, will contain two things. It will contain a value, and it will contain a link or a pointer to the next node in the list. The idea being is that we have some kind of start of a list, so you could in some implementations have a head to a list, and that head node will point to the first element of the list. That element or node in the list will contain a value in addition to a pointer to the next element, and so on and so forth. Now, the way we've decided to implement the list or a linked list in our context is we're not going to explicitly have an independent head. Instead, we will treat the first node in the linked list as the head of the list. So that will have certain implementation constraints that will impose upon us, but we'll discuss that as we go through. And in our example, we'll treat the null pointer to indicate that we're at the end of the list. So if your next value in a given node is null, it implies that that is in fact the end of the list. We do this by indicating the null value as a simple 0, meaning that I'm not pointing to anything. Okay, this is how we're going to try and implement our linked list for this course. Now, I should mention that the data type that will be present in our nodes are going to be of type long. Obviously, we could generalize what we're doing here. The reason I've chosen to use long is because obviously long is 8 bytes, and the way we've constructed our nodes, we get a nice alignment properties if we simply use a long for the value and we have our pointer to the next node, because then we have 8 and 8 bytes, so we have a 16-byte node object, which means alignment is trivially sorted out for us. Okay. Now, something that I have to mention before I continue is I mentioned that because we are utilizing the first node in our linked list as the start of our list in this implementation, if I were to insert something into the list at the front, it would imply that the start of my list has changed. Now this means if some other part of your program has a pointer to this list, it would have to update that pointer if I were to insert in the front of this list. So obviously a downside of having an implementation where the head itself is not an independent component to the rest of the list. So with that in mind as well, the way in which we'll do inserts to start with is we will always insert at the front of the list. Obviously this is going to be quicker than inserting at the end of the list. If we were to insert at the end of the list, we'd have to traverse through the whole list. So by inserting at the front of the list, we simply replace or create a new node, link it all up from the start. And I'll go through that in detail now, which is obviously more efficient than adding at the end of the list, given the fact that we don't have a tail node stored in any way. So this is going to be our node structure that we're going to be using. Again, I'm utilizing the struct pseudo ops available to us in assembler. I'm going to call the struct node, and inside it I'm going to have two values. I'm going to have the actual value that the node will hold. So in the previous slide it would be, for example, 12, 4, 16, or 19. And then I'm going to contain the pointer to the next item in that list. Now, we could obviously have a situation where I point backwards to the previous item, but then that's no longer a singly linked list, and we'll get to that later where we have a doubly linked list where we have the back and forward linkage. But for the moment, we simply have a forward linkage present in the system. Now, first thing that we're going to implement here, it's relatively trivial, is we want to construct a function that will return to us a new list. Now, the only reason we're actually implementing a function like this is because if we were to decide to change our implementation such that we do in fact have a leading head node that is not part of the linked list itself, we could just simply change this new list. However, as we've discussed, the list itself will simply point to the first element inside our list. So that's what will be returned from this. And since we have no items in our list to start with, we actually simply return back an empty reference. So, or a null pointer. So I will simply XOR EAX. The only reason we're XORing EAX again here is it's simply a shorter instruction, but we are actually working with the full 64-bit null value. We then return it, and if I want to create a new list, all I have to do is go call new list, and I will take the pointer to my list, or my first element of my list, and load it into some data segment memory. Obviously I could put that elsewhere, but this is just for illustrative purposes. But the important thing to note here is there's nothing really happening here other than the fact I'm actually loading the value 0 into the list. That's truly what's happening in this case. However, the way we've done this is if I were to change my structure of my linked list, I would only have to change this function really. Now the next thing we need to do is we need to discuss how we can insert into our list. Now we've already made the decision that we want to insert at the front of the list, so our list is in essence an unordered list. It's only ordered in terms of insertion order, where the most recently inserted item will be at the front or the head of the list. The way in which we will construct our insert function is as follows. We will have a function called insert. It will take two parameters. It will take a pointer to the head of our list, which will be the first element in our list, and we will specify the value we want the newly created node to have that is going to be inserted into our list. Now, note here that we assign the result of this insert to list. This is because I'm replacing the first node in the list, and that is how I actually refer to my list as a whole. So if I add an element in, my newly created node is actually going to be the one where the user would have to access the linked list via. This is obviously a downside of this approach. However, it's an approach that the book has used, so we're going to stay consistent with that. So after I insert a new item, I'll return back a pointer to the start of the list, and then the user can continue working with the list as they choose. Now, if I were to call this function in my assembler code, all I would have to do is I'd first pass through a pointer to my list into RDI, which is obviously the first argument when you call functions. Then I'll pass through, in this case, K, which will be something in our data segment, which will be a long, in our case that will be a data quad, and I'll pass that through to RSI. Then I'll call insert, it will create a new node for us, and then it will add it to the linked list, and it will then return to us a pointer to the start of the new list. Okay, which means that the return value of insert will be in RAX, and if I want to save that back to somewhere in my data segment, I simply save it back from RAX into list. Now that we've discussed how we want to implement insert, or how we want insert to function, we should implement it in assembly explicitly. The function here now is our insert. First thing to notice is that I have specified two EQU ops. Specifically, I'm adding the constant here, so I have the offset for list and the value which I wish to insert. This is because I'm going to be calling functions inside this function, and I want to maybe be able to preserve these two values while I make that call. Specifically, when I get given the list and the value, I know I need to create a new node. So I'm going to make a call to malloc in order to create that new node. Now, given the fact that I'm going to call malloc, I would like to have the pointer to the list and the value that the new node should contain saved somewhere when I actually make that call to malloc. So this is why I'm going to be storing two things on the stack. Second thing to notice again is I'm going to be setting up my stack frame with these two lines over here, and then I'm going to be destroying it over there with this leave command. Reason I need to set up and destroy the stack frame is I have the intention of calling another function. Specifically, I want to allocate the memory for the node itself. Then, next line is I'm going to subtract 16 from RSP. This is making space for my two stack-based variables. Specifically, I'm going to store the first parameter on the stack using the offset.list. Specifically, that will be with the offset of 0. And then I'm going to store my second parameter, which is k in this case, which would be the value that I want my node to contain, into RSP plus k. So it will be based on the offset of 8 on the stack. So now those two values are nice and safe and secure on our stack, so I don't need to worry about losing them when I make a call to my malloc function. Now I wish to actually call malloc. So first thing I'm going to do is I'm going to load the size of my node into RDI. If you remember from our previous lecture, this node underscore size is a nice pseudo-op which will do the pre-calculation of how big our struct object is actually going to be. So we know that we'll have the correct size loaded into RDI. Now RDI again obviously is the first parameter of a function. We're then going to make a call to malloc, which will now allocate us the number of bytes that we have specified in RDI. In this case it will be 16, because that would actually be the size of our node object. Once I've retrieved this object, I then want to retrieve, before I assign any values to it, I want to retrieve the values that I've saved on the stack. Specifically, I want to get back the pointer to the list, so I'm going to move this back from the stack space storage to R8. No specific reason I'm using R8, just that I happen to choose to use R8. I'm also going to retrieve the value that I've saved on the stack, the value which I want to store in the node. Once I've retrieved those two, I can now assign them to my newly created struct object. So I'm going to assign R8 to the next value in my struct. Now basically what this means is that I'm going to have my newly created node point to the old start of the previous list. So I have my original list, I could then add my new node, and then that new node will point to the start of that old list. Then I'm going to take this newly created node and return it back to the person that called insert, which means now they will have a pointer to the newly created node, which will point to the rest of the old list. Now, just to maybe clarify things a little bit, if we look in this graph here, I end up having a pointer in RAX, which you can see specified there. I have this pointer that's in RAX, and that is going to point to the start of my struct. The struct has been allocated such that it's 16 bytes, and if I add an offset of, for example, n underscore value, I will end up adding an offset of 0 to the pointer that RAX holds. Then I can specify whatever the value was. Let's say 13 was the value that we wanted to be stored. And in the same kind of fashion, if I want to change what the next pointer is, or the pointer to the next node, I can simply gain access to that by going RAX plus n underscore next. So it will take the pointer that I got back from malloc, add the offset of 8 to it, and then I can set its new value. Now I thought I'd just add this little depiction to make things maybe a little bit clearer for you if you're a little rusty with how to work with stacks still, or structs rather still. Okay, so now that we have this in check, so the first thing, as I mentioned, is I'm going to store the pointer to the old list in RAX underscore plus n underscore next, and then I'm going to save the value k into n underscore value. Okay, so my new node object's values have been filled in. Then I can simply return, and this will return RAX, which is again pointed to our first node of our new list, and it's also going to be the pointer in some sense to our newly created node. So now that we've discussed how to insert, the next thing that we need to discuss is how we can maybe print the list. Now obviously the reason we're going through a print function explicitly is just to give you an indication of how you could iterate through the list as a whole. So our print function is relatively straightforward. I'm going to have obviously the print function name, and this function will simply take one parameter, which will be the pointer to the list itself. I'm going to set up my stack frame with these two lines over here, and this is because I intend on actually calling another function inside this. Specifically, I'm going to call printf. Now, this is something that's a little bit different. Instead of using stack-based storage, we have decided to try and utilize a register that we know is safe across function calls. Specifically, I want to try and save the first parameter into R12. Now, I know when I call another function like printf, R12 is not going to change. R12 is not going to change. I could achieve the same behavior instead of using the call save register by simply using stack-based storage, but you'll see when I go to the next slide that I'm going to be making use of R12 quite frequently inside a looping structure, which means this is a slightly faster approach. Obviously, if you're in a test, I think go with the approach that you're more familiar with. Don't worry too much about the speed aspect. But that's the justification for why in this case we are actually preferring to try and use a register safe or a call safe register. Now, because we want to try and use a call safe register, I need to ensure that I conform to the same agreement that R12 will remain unchanged when somebody calls my function. So because I'm intending on using R12, I need to preserve the old value R12 had. So I'm going to then push R12 onto the stack. So now it's safely on the stack. And once we've finished with our execution, I can simply pop the value back off into R12 and then return. So everything is set up for us to use R12 across internal function calls. We're going to quickly define a little data segment here. This is just the formatting of our printouts. Specifically, the first one is the print format, where I indicate I'm going to be outputting a long. That is all this LD indicates. And the 0 there is because this is obviously going to be a null terminated string. This PRT underscore NL is just to indicate that I'm going to print out a new line when I actually print that specific label. Moving into the function itself, we start with a while loop. And what we are doing in this loop is very straightforward. I'm going to compare R12. Remember, I've saved the value of the list, or the pointer to the list, in R12. If R12 is equal to 0, it means that I'm currently at the null pointer, which means that I am actually at the end of the list, or in the trivial or most trivial case, the list was empty from the start. And if that is the case, it means that I have no more items to iterate over, so I can simply jump over the rest of the loop. So let's assume that happens to start with. I'm going to have a comparison against 0. It matches, so I'm at the end of the list. I'm then going to jump to the end of my loop. Once I'm at the end of the loop, I'm going to proceed, and then I'm going to move the address of PRT underscore NL into RDI. I'm going to set EAX to 0 and then call printf. Just as a reminder, this RAX being 0 indicates that there are no floating point parameters for printf. And the first parameter for printf is going to be in RDI. So this is just going to simply print out a new line. There's something that is present in this code snippet that you have not potentially seen before, and that is the way in which I'm referring to the label. Specifically, I'm using print.prt underscore NL instead of, for example, .prt underscore NL. Now, the reason this is possible is because it is using this print as a more global identifier or a more global layer, and these dot labels as subsets of print. So specifically, I'm telling the assembler that I want to go to label print, and from there I want it to scan to the first place it finds a match. So it will look for print, and then it will scan down, find .prt underscore NL in this case, and then it will return that address. This is useful, obviously, if you have a single file where you have multiple functions present. So now these labels are specific to this function. Obviously, if your examples are very small in tests and stuff, you don't need to worry about it, but I thought I'd just mention why this is actually functioning the way it is and potentially the way you could use it in future. So let's now assume we are not in the trivial case and we actually have items still to iterate through in our list. What we are going to do is I'm going to move the format of my output. Specifically, I just want to output a long. I'm going to move that into RDI, and I'm then going to move the current value of my current node into RSI. Now remember, R12 contains a pointer to the current node, and then by adding the offset of n underscore value, we are now accessing the part of that struct which contains the value that that node itself stores. So it could be the value 3 or 7 or something along those lines. That value is then moved into RSI. I'm going to XOR the EAX register, so this is basically setting RAX to be 0 again because we have no floating point parameters. Then I'm going to call printf, and we will output that specific value to the screen. The next thing that we do in this loop body is the important part, is that I'm now going to set R12 to be the dereferenced value of R12 plus n underscore next. So all this is basically doing is I'm taking what R12 points to, I'm adding the offset to get to the next pointer. So what is contained in these square braces is basically the location of the next pointer. By adding the square spaces, I will dereference it, and that means I will be passing that pointer itself back into R12. So now R12 will contain the pointer to the next node in our linked list. So this is how we're performing the iteration as such. Then once we've moved to the next element of our node, or next element of our linked list rather, we are able to jump back to the top of the loop body, and we can proceed in this fashion again and again until we end up with the point where we've hit the end of the list, or more specifically, we are now pointing at the null address, or the address of 0. Once we've done all of that iteration and we printed our new line character, all that is left for us to do is to simply pop R12, because remember we pushed it in the beginning to save its original value. So we want to retrieve that original value from the stack, so we pop R12 so it goes off the stack and back into R12, and then I will destroy my stack frame and return from my function. Now, you can note by looking at this loop body that it would be possible to, instead of using R12, work entirely with stack-based memory. However, you can clearly see how many times I will have to be putting something onto the stack and off to the stack. I will have to, at this point here, retrieve a value off of the stack, make my call to printf. Over here, I will again have to retrieve the value from the stack and alter it, which means that I'm going to have this continual procedure of going off and on the stack, which becomes, or makes your function somewhat more complex and adds an extra one instruction to the actual execution, or 2 instructions to the execution rather. However, again, don't worry too much about the performance aspect, but I'm just illustrating that there would be a meaningful difference if I were to just use the stack-based storage instead of using the call safe register. Now that we've implemented our print list function, it would be useful to try and construct a more full-fledged utilization of our linked list object. So what we're going to do now is we're going to implement a small little main program that will take in a user input. Specifically, it'll take in a user long input, or an integer long. It will then add that integer to the front of a linked list and then print out the whole linked list. And it will repeat this process until the user has inputted an invalid value. For example, if the input or the user inputted the value of E, the program then would terminate. So that's what we're going to now try and implement. So first thing is we have our main function label, and then we're going to specify 2 EQ pseudo ops. Specifically, we're going to specify list and k. Just as in the previous situation, I want to have a nice safe space on the stack to store these 2 values when I make calls to other functions. Now in our case, we're going to be calling a couple of functions. We're going to be calling scanf because we want to try and read in a value from the terminal, and we're also going to be potentially calling functions like creating a new list or adding to a list and so on. So there's quite a few functions we're going to be calling, so it's good to have that nice location to store these values on the stack. What we specify here in the data segment is simply the scan format. Again, this is just to indicate that we're going to load in a single long from the terminal. That's all we're trying to do with our scanf, nothing too fancy. So moving on to the function body itself, again, because we plan on calling other functions, I'm going to set up and I'm going to destroy a stack frame. I know I mention this quite frequently, the setup and destruction, but I do it intentionally because it's something that is so vital to ensure that your functions actually work correctly when you try and link them up with languages like C and C++. Again, because I mentioned I want to store those two values on the stack, I'm going to minus 16 from RSP because I want to store two data quads. And luckily for us, 8 plus 8 is 16, which is a multiple of 16, so I don't have to worry about any alignment concerns in this case. So we've set up our stack frame, we've given ourselves a little bit of space in the stack to store those two values. I'm going to now call my new list function, and this will again return to me the pointer to the list or the first item of the list. Now, if you remember from slightly earlier in the lecture, all this is actually doing is it's returning to us the null value to start with. I'm then going to take the value that I got back from new list and I'm going to save it on the stack. So now the stack at the location or the offset list will store the pointer to the first element of our linked list. If the linked list is empty, as it is in this case, it will simply point to null, but we will utilize this location on the stack to always point to our linked list. I'm then going to load in the scan format to try and utilize scanf. So I'm going to use this by using LEA, and then I'm going to move the scan format into RDI. Now, it should be made clear that I could have done this operation just as well by using MOV and then using RDI, .scanf underscore FMT without having to have the square braces, both of which would have worked fine. However, the next line, there is a very good reason that we're using LEE as opposed to move. What I'm doing here is I'm basically passing into RSI the address that we have on the stack where I'm storing K. K in this case will be the current value which I'm trying to read in from the user. So what RSI will contain is it will contain the address that RSP plus the offset of K will represent. Now if I were to try and just replace LEA with move, this operation would not assemble because it will not recognize this RSP plus .k. It only works in the context where we have dereferenced braces. So that's why we are utilizing this LEA in this case. That's an important thing to try and get comfortable with and why we chose to do this. It is, of course, possible to not use a LEA at all, but then you end up having to use two instructions to achieve the same result with moves. So the LEA actually works out simply. The next thing we're going to do is we're going to set RAX to 0 by XORing. And this is because our scanf function needs to be told that it's planning on reading no floating point parameters. I'm then going to make a call to scanf. And ideally, if the user input a single integer value, it will be loaded into the address that I've pointed to in RSI. Now, something that is important to note about scanf that you may not be overly familiar with is that scanf returns an integer. What this integer represents is the number of successfully loaded parameter values or successfully loaded arguments. So in our case, if everything went right, scanf should return the value 1, meaning it correctly loaded one input from a user. If scanf returned 0, it implied that it failed to actually correctly load that argument. So what we are doing here is we're checking, based on the number of correctly loaded arguments, whether or not scanf worked successfully. So if when we compare RAX, which is the return value of scanf, if we compare it to 1 and it is equal, it means we got in what we expected. If we got in something other than that, something either went wrong or the user, for example, simply inputted a character, which means it would have failed to load into what it was expecting to be a long. Now, this is a nice way of us having a terminate condition. So if the user at any point inputs something that is not actually an integer, we end up terminating this looping process. Okay, so we don't need to do a check for if they input E specifically. In this case, if it's any invalid input, we'll end up terminating. So let's assume that we are in a situation where Rx is not equal to 1. So say the user immediately inputted the value F, for example. Then RAX will actually be the value of 0, and then we'll be comparing 0 to 1, and then when we check are they in fact equal, well they're not equal, then this jump NE will jump to the done label. We'll then destroy our stack frame and return. So we've done with execution. If we're in a situation where the user is following the instructions correctly and he's inputting a reasonable value, what will end up happening then is this comparison will yield that they are in fact equal. This jump will not fire, and then we can continue to execute the rest of our code. The first thing that will happen if we got in a valid value is I'm going to retrieve my list pointer from my stack. I'm going to load that into RDI, and I'm going to retrieve the value k that I got from my scanf function. Now remember that when I passed values to scanf, I passed the address on the stack to scanf. That means that once scanf has completed, it will load the value that it has gotten into that location of that address. So specifically, it will load directly onto the stack the value that it read in. So we take from that address, we dereference it again, and we retrieve the value that we just got from scanf. So now RDI will contain the pointer to our list, and RSI will contain the value that we just read in. The reason we have to retrieve the list is obviously when I call scanf, the value that was in RDI is most likely been changed. And even if it wasn't changed in this example, it would have actually held the address of the scanf format. So we need to retrieve this and put it into RDI. Specifically, the reason we want to load in RDI and RSI is I want to make a call to the insert function. Now the insert function, if you remember correctly, has two parameters. The first is a pointer to the list. The second is the value we wish to insert in the list. And it's going to return the pointer to the start of the list after we have actually added our new node. So we load the needed values to do an insert. We call insert. We then get a pointer back to the start of the list. I want to save this on the stack. So I'm going to take it from RAX and I'm going to save it back into my list variable on the stack. Then I'm going to move RAX into RDI, and the reason I'm doing this is because remember I said I wanted to print out the linked list after every new addition, just so we can see everything's working fine. So I'm going to move the value from RAX into RDI, and then I'm going to call print. Now print will take the pointer to the list and it will iterate through it like we designed it to, and will output all of that to the screen. Once we've printed out to this, we'll print it out to the terminal. We'll then jump back to the top of the loop body, and we'll continue this procedure again and again and again until we end up having a failed scanf statement where the user has input something that's not along. So just to make this operation a little bit clear, I think it's informative to maybe look at an example output. If, for example, the user inputs the value 4, then what will be output is the value 4, because the linked list only contains one value, specifically 4. If I now add the value of 5, the linked list that will be output will be 7 and 4. If I give the next value of 7, it will then be 7, 5, 4, and the procedure continues all the way down. So what this implies is that, say we're in this line over there, the linked list itself contains the values 1, 4, 6, 2, 1, 8, 7, 5, 4 in that order, from this being the head and this being the last element of the linked list, or the tail. When the user inputs a value that is not a double, for example, F now, the program itself will terminate. So this is how we've illustrated that the linked list itself is functioning. Now that we have a good understanding of how to implement linked lists in assembler, I want to give you a little bit of homework. Specifically, I would like you to try and think of how you could implement a deallocate method for list. So say, for example, the method would take in one parameter, which would be a pointer to the first element of the list, and then it will incrementally go through the whole list and deallocate every single item. The other little bit of homework I want you to do is I want you to try and think of how you would implement the same function, or the insert function, however we want the list to remain ordered. So the idea basically is you can use the insert function that we've already discussed as maybe a helper function, and have a more intelligent insert approach such that the list has a preserved order. Say, for example, an ascending order, for argument's sake. Now, I mentioned these two homework examples because I might, in the exam, ask one of these two things as a sub-question. So you can take that hint as you choose. Now that we've discussed singly linked lists, we can move on to our discussion over doubly linked lists. Obviously, there's nothing fundamentally different between the two. However, it gives us a little bit of extra freedom in the way in which we will add and remove nodes from a doubly linked list. There's obviously also the compromise that a doubly linked list will require more space than a singly linked list. Now, the way in which we have chosen to implement the doubly linked list is to always actually have a head node. The head node itself will not contain any other value other than the fact that it is a head node. So an empty list in our implementation will always contain one node. Specifically, this will be the head node. Now, this should be distinct in your mind between the way in which we've chosen to implement a single linked list or singly linked list. Now, obviously, this is not something that one has to do for doubly linked list. This is simply the way in which we're going to present the doubly linked list, which is in accordance to the way the book has discussed it. So I don't want to deviate too drastically from the book's material. Now, to make things a little bit easier for us as well, we've decided to have not only a doubly linked list, but a circular doubly linked list, which makes insertion pretty trivial, and it also makes it easy to insert from either the front or the back, because you can technically get to the back of the linked list from the head node, seeing as though it's actually a circular list. Now, there will be 3 attributes stored in each node in our doubly linked list, specifically the value we wish to store. Again, we're going to be storing longs in the node. Then there are 2 more parameters. It's going to be the next pointer, which will point to the next element in the list, and the previous pointer, which will point to the previous element in the doubly linked list. So there's the 3 components that we need to have present. So the way in which we define our struct is very similar to the previous situation. We now have a value like before, and next also like before, and the new attribute is now this n_prev. Luckily, again, we have 3 quad words, so we don't have to worry about any alignment concerns. Alignment is implicitly sorted out for us. Something to note in this context is that an empty list will also itself be seen as cyclical or circular. Now, the way in which you can see this is that if I have my list, it will point to my head node, which will contain no other value than simply being the head node. We will then have its next pointer actually point back to itself, and its previous pointer also point back to itself. So that's how we've decided to implement our empty list. Okay. It makes it easier to work with in the sense that we don't have a special case such that when we only have just a head, it is no longer circular, but when we have elements, it becomes circular. In this case, it is always circular, so it makes it a little bit easier to deal with. Now, to implement our new list function, it's relatively straightforward. First, we need to set up and destroy our stack frame, and that's because we plan on calling a function, specifically malloc. I want to allocate a chunk of memory that is of size node_size, again relying on the sudo op. So in this case, node_size is going to have the value of 24, so we're going to allocate 24 bytes for our node. So we're going to load 24 into RDI, and then we're going to call malloc. So it's going to now return to us a pointer to some contiguous piece of memory that is 24 bytes long. Now, inside that contiguous memory, I want to set a couple of values. I'm going to set the next value to point back to that item itself. So basically, the head will point back to the head, and I'm also going to have the previous value point back to itself as well. So the head going backwards this time will also point to itself. We don't specify the value for our purposes now. It's immaterial. We will refer to the head by the location that it is inside the list. Specifically, when I pass through a list, I will always see the first element that I'm pointing to in that list as the head, and you'll see how we'll use that later on. So we don't need to store any value to indicate that it is in fact the head node. So that's why we don't bother specifying it here. Now, obviously, one of the important things, at least with the doubly linked list, one has to come to grips with is how we try and insert and delete from a doubly linked list. So we're going to go through the insertion in this example. However, I would like you to also be able to implement this yourself for deletion. So I think it's important to go through this example quite carefully and then figure out how you could do the reverse operation by deleting a specific node, even if it is only, for example, to delete the first node other than the head node in our doubly linked list. Again, something I may ask in an exam. It makes for a nice exam question. Now, the way in which we can do the insertion is quite straightforward. The way we've decided to do insertion as well too is insert at the front of the linked list. Specifically, if this was my linked list over here and I wanted to add a new item, I would be adding it in between the X and the 4. Now, the way in which we insert an item into a doubly linked list requires a couple more steps than with a singly linked list, and that's because there's a couple more things we need to link back up correctly. Because in some ways, when you add a new element to a list, you have to break the old links and then reattach it to make the linked list function again. So let's assume that this 4 was not present in our linked list. So that would mean that this X, which is our head node, would have its next element or next cell point to this node containing the value of 12. By the same token, the previous element of this node or previous value of this node will point back to the head node itself. So let's assume we're in that situation. So X points to 12 and 12 points to X. And now we want to insert 4 into our array, or our circular linked list rather. So the first thing we're going to do is we're going to make the new node's next point to the head of head's next cell. All that means is what head used to point to is what our new node should now point to. So the next of the head will now become the next of our new node. The next thing we have to do is make the new node's previous value point to the head cell. That's because, again, we decided we want to insert at the front of the list. So then all I have to do is I need to set the previous pointer of 4 to X. So it just points back to the head node. Now, there's two links that are still missing in this situation is that we don't have that link from the head to the 4, and we don't have a link from 12 to 4. So what we have to do to achieve that is we have to make the head's next cell point to the new cell. That's very straightforward. We simply add that link. The last link is where students often forget to make the link correctly or have a bit of trouble deducing where they have to change the link. However, if you look at this picture, it's actually quite clear. What you need to do is you need to change the previous pointer of the new node's next node. Specifically, if I add 4, I know 4's next node will be 12. I now need to change 12's previous value to point back to 4. So the way in which you do that is you make the new node's next node's previous cell point back to the new node. Sentence sounds complicated, but if you look at it diagrammatically, it's very clear what we're actually trying to achieve. So let's try and implement this in assembler. So the first thing we're going to do in my insert function is I'm going to set up my stack frame and destroy it as normal. Just something that I should mention here, the way in which the textbook has chosen to implement this insert is slightly different than the single linked list insert, in that this insert doesn't necessarily have a return value that corresponds to the head of the list, which means that you will still use the previous value you had for that list even if you made subsequent inserts. I can also indicate in this, once we've gone through this, how you could change it to make it work the same as our single linked list example. But just keep that in mind because it's not explicitly stated in the textbook that that happens. Okay, so we set up a stack frame. I'm then going to allocate space for 2 quad words on my stack. And again, let's assume that I have defined 2 EQ ops again for list and k, where list will point to the list itself that I want to try and insert into, and k will be the value I wish to insert. I'm just adding or saving a little bit of space by not redefining that. So first I'm going to move the value from RDI onto my stack, so I'm saving my list. I'm then going to move the value in RSI again onto the stack to save it. So I want to make sure that those values are nice and safe on my stack when I make a call to an example function like malloc. Next thing I'm going to do is I'm going to allocate my new node, and I simply do that by moving node underscore size into RDI. Again, that will allocate 24 contiguous bytes of memory when I call malloc. Malloc will return the pointer to my newly allocated memory in RAX. So now we have our newly allocated node, and we need to try and redo all of those connections that we discussed in the previous slide. So let's go through these lines carefully. The first line here is going to retrieve the actual head node of the list that we passed through and store that in R8. Okay, so we're just getting that back from the stack. The next thing that we're going to do is we're going to get head's next node, and we're going to save that in R9. So what that means is I'm taking a pointer to X and I'm saving it, and I'm taking a pointer to this 12 node and saving it. So I'll have the head and what will be the next node of my newly inserted node. So these two we have now set. So we have a pointer to this one and a pointer to that one. Then I'm going to set the next attribute of my currently newly created node to R9. And all that's doing is that it is setting the link between this 4 and 12. So it's producing that little arrow for us. Then I'm going to set the previous value of the newly created node to R8. And remember, R8 was actually our head. So that's simply making that link over there that we've now added. Moving further down, we now want to try and change some of the links with respect to the new, or change links with respect to the old head and the old head's next value. So what I'm going to do is I'm going to set R8's next to RAX. So specifically R8, remember, is the head. So I'm going to change the head's next to be my newly created node. So I'm simply adding that arrow over there. Next thing I'm going to do is I'm going to specify that R9's previous is going to be RAX. And remember, R9 was actually the old next of my head node. So I'm going to be adding this connection from the old next from head. I'm going to set its previous value to point back to 4. So as you can see now, after we've done those lines, I've added all of the corresponding links that I need to effectively insert this new value. The last remaining thing we have to do is we have to actually assign the value to the newly inserted node. So we've got that value passed into us from the argument list at the beginning of this function. Remember, it came through in RSI. We stored it on the stack at the offset k. And I'm just going to simply retrieve that, set R9 to it. Again, no specific reason I'm using R9 again. And then I'm going to take the value from R9 and I'm going to store it in the value location of my new node. So this is me setting the value. So say, for example, k was 4. Now the value of my newly inserted node will be 4. Okay. So hopefully this has cleared up how we can do all of the connections. The important thing is to be able to look at this code and make sure you can see at each location what line am I linking up. Once you can figure out what's happening with that, it becomes very easy to interpret this assembler code. Just as a quick sideline note, the reason that these two move instructions are in two separate moves is, remember, I cannot make two accesses to memory using this square bracket notation. That's why I have to separate this into two instructions. Okay. Now, once we've been able to insert into our function, another thing that would be useful to do with our doubly linked list is to be able to print out all the elements as well. Now, in that context, we are a little bit restricted in that we don't have a nice null value to indicate that we're at the end of the list. So the way in which we are going to try and indicate that we've reached the end of our circular list is when we get back to the head node. So that's the idea, is that we'll start printing each item in the linked list. So we'll start printing each item in the linked list until we get back to the head node, and then we stop. Okay, so that's the plan of action with this print function. So here we have the prototype again, and set up stack frame as usual, and destroy stack frame. Now, something might appear a little bit confusing is I'm going to be using R12 again because I know it's call safe. But instead of simply using push and pop, I'm going to store it onto the stack. Now, you can do what is present over here by just using pushes and pops. However, it can get a little bit confusing if you're not very familiar with it, and that is because I want to have a second variable also on the stack. Now, if I were to have a command over there like push R12 and then have a command like this move, everything will be fine, but when I get to the end of my function, I need to ensure then that I, for example, first remove this variable before I pop back the variable for R12, which can get a little bit messy to try and determine that you're doing it in the right order. Obviously very doable, but it just confuses matters slightly. So we've decided to do all of our stack-based storage in this unified manner of just simply moving it onto the stack using these move commands with offsets. So we're going to save the old value of R12, because I plan on using that register as a call safe register. So I'm just making a backup of its original value. Then I'm going to save RDI into the list variable on the stack. This is again because I'm going to call functions and I want to make sure I can retrieve that list pointer. Once that's done, we now need to start our iteration process. So the first thing I'm going to do is I'm going to set R12 to be RDI's next. Okay, so basically the node that RDI points to, its next value, I'm going to set R12 to that. Okay, so I'm going to move one up in the doubly linked list. So I'm simply moving from here to here with the value that is in R12. Then I'm going to compare the value in R12 with the actual pointer to the list that I retrieved. Now, if the head's next is in fact the head itself, these two will be equal, because I'm in a situation where I am referring directly back to the head. So the head's next is in fact itself. That's what we're doing in that comparison over there. Okay, so we first do that comparison there to check if basically we have an empty list. And if these two are not equal, we're in a situation where we don't have an empty list, and we're currently at the first real element of our doubly linked list, which is pointed to by R12. So now we're in our actual loop body. I'm going to move then the print format into RDI. It's the same print format we've been using up until now. It's simply to output a long. Then I'm going to move the value that is in my current node. Again, I'm just simply using the internal offsets. So I'm going to obtain the value that is in my current node and move it into RSI. I'm then going to specify that I have no floating point parameters and then call printf. And this will output that value to the screen. Okay, so it's just going to output the single element of our doubly linked list. Just as a note, if you're comparing the slides with what is present in the textbook, this XOR and this XOR are not present in the book. They should be, just if you were curious as to why they were omitted in the textbook. I think it's just a simple error that has survived through the additions. Now, once we've actually printed out our current node's value, we want to try and iterate to the next value. We do a very similar procedure that we did in the single linked list. I am simply going to set R12 to be R12's next value. So I'm just going to move up in the linked list. Then I'm going to do the comparison between R12 and the list itself. So basically this is me checking, am I at the head yet? If I am at the head again, then I know, okay, well, I've reached the end of the list. So if it is equal, then I can simply continue out of my loop body because I've exhausted the entire list. If that is not the case, I will realize that, okay, well, R12 is clearly not the head yet, so I'm then going to jump back up to more and repeat this process again and again and again until I end up getting an equal comparison between R12 and the list. So I've gotten back to the head. Once we've gotten back to the head itself, we now need to simply output our new line character just to move the terminal down one line. I'm going to move the new line format string into RDI, and again, no floating point parameters, and then I'm going to call printf. This will just add the extra line. Finally, I'm going to restore the value that I had saved on my stack for R12. So I'm going to move this back from my stack-based storage onto R12 and then leave and return. Now observe that if I had specified over there pop instead of the way in which I specified it here, there would be the issue of, if I specified push in this line, I would have the issue that when I call pop over here, it will not pop the value that I saved for R12, but rather it would end up popping the value of a list, which is clearly not what my intention was. By doing this way, I'm ensuring that I'm restoring the correct value for R12, and then I can destroy my stack frame and return. Okay, something that's important to note. It's a little bit subtle because it's the first time you've seen us use call safe registers in addition to stack-based storage. Something that I promised that I would explain in the previous insertion slide, which I did actually forget, is I mentioned that with this insert function, the way it works currently is it doesn't need to return anything. It doesn't return back to us the pointer to the head. If I wanted to change this function to operate in that way, all I would have to do is move the correct value back to RAX, because currently RAX has the pointer to the newly created node. So all I would actually have to do is I'd simply have to move into RAX plus in underscore prev. So I move back the previous value of my newly inserted node into RAX, and then this insert would function the same way in which our single linked list insert also operates. So that's how you could change it to correspond to the previous version. Okay, so that brings us to the end of our doubly linked lists. The next topic we're going to be covering is hashing tables. The hash tables that we're going to be discussing in context of assembler are going to be relatively simple. In some ways you can see them as toy hash tables. And by that I mean that the only thing that will be stored inside the actual hash table will be the keys themselves. Obviously, if you were to implement this in a more general context, you would probably want to store something in addition to just the key. But for simplicity's sake, the only thing we're going to be storing in the internal nodes is actually the key. Now, generally speaking, a hash value defines an index in an array where we wish to store the key. Obviously, there's the issue that it is possible that we will hash two distinct keys to the same index in an array, and then we have to deal with what we call collisions. Now, from COS 212, I'm sure you're well aware of various ways of handling collisions. For the sake of this section, at least, we're only going to deal with a single linked list being the way in which we handle the collision. So instead of only having a single item in each element of the array, instead, the element of the array will point to the start of a list, and it will point to all subsequent keys that actually had the same hashed value. So this is how we will treat collisions in this context. Now, a good hash function generally will spread the keys around. Now, obviously, outside of the scope of this course, there is a huge array of possible hash functions with a lot of theoretical properties known that have been derived. However, for our purposes, if we're trying to have a hash function simply for integers, so we want to map an integer key to an index in our array, the one that we'll consider using is the most basic hash method in some ways, and that is to simply mod. The idea being I take the integer k, I mod it by t, and the answer of that calculation is my now index in my new in my array itself, where t, generally speaking, is going to be the table size itself. Now, this kind of hash should be sufficient for our purposes. Now, obviously, there are weird issues where if there's a relation between the kinds of keys you're going to get and the hash table size, you could get weird clumping that is obviously not ideal. Again, not something that we're really concerned with in this course. That's more of a concern of a data structures and algorithms course. Now, a good recommendation often is to use t to be prime. However, in the assembler context, we're going to use a nice simple trick to build a nice little hash table. Specifically, we're going to set t to be 256. So we're going to have a table of 256 entries. And because we have a table size of 256, we can perform this mod calculation in a very clever way. So here we see our hash function. What it does is it takes in our key, which is this n, and will return back our index. Now, the first parameter that we get in is obviously going to be an RDI. I'm going to move it from RDI into RAX, and then I'm going to AND what is in RAX by FF. Now, what this is doing, if you remember from our lectures quite a while ago with bit operations, is that I will in essence be selecting the bottom 8 bits from my actual key. Now, you can see if you work through an example that is basically the same as chopping off everything that is higher than the 256. So it's a nice way of modding. You can also see that the same thing will actually work nicely if we end up having negative mods. So for example, -4 mod 256 will end up giving us the answer of 252, okay, which is what we would like to expect. Now, meaning that it goes the other way around in this case. So that's just something to keep in mind. So this is our hash function that we could use if we wanted to hash integer keys. If we wanted to try and hash something a bit more complex, for example, a very common thing that's used for keys is strings. The most prevalent approach for hashing, again, it's one of many, is to evaluate a polynomial where the coefficients of that polynomial are actually the characters of the string you wish to hash. And then you will evaluate that polynomial for some given x. Okay, in our case, we will use the x of 191. Which is simply a prime number, and generally speaking, there's a bunch of calculations that exist to indicate what primes are good given the size of your potential strings and things of that kind. Again, not a concern for us. So for the moment, we're going to use this polynomial approach where we'll evaluate the polynomial at 191, and the coefficients of that polynomial will be the characters of the string. By that I mean that if I have a character like a, I will times its ASCII integer representation value. By that I mean if, say for example, we have a character like a capital A, that would correspond to the decimal value of 65 if you looked up in your ASCII table. So that's what I'd be using as the coefficient that corresponds to the letter A. And say for example the next character was a B, then that coefficient would be 66 and so on. Now, a very common way in which people can compute this kind of hash is to rely on what's called Horner's method for calculating polynomials. That's what we have present in this little function over here. So a couple of things I just want to mention, that in this hash example, you'll see that we'll mod the result by 100,000. That's simply because in our case we've decided that we want to have a maximum table size of 100,000. Now obviously that means we're going to occupy a fairly large amount of space, but that's not the focus of this discussion. It's more just to show you how we can do this kind of stuff in assembler. Now, just to give you a bit of an inclination of what Horner's method is simply a nice way of calculating the polynomial value, but what it does is it reduces the amount of multiplications you have to perform. The way you can envision how this would work is if I needed to calculate something like x to the 10. Now, in order to calculate x to the 10, I would need to times x by itself 10 times, so x times x times x, and so on. However, if I also needed to calculate x to the 9, I would have preemptively calculated most of the multiplication necessary to actually calculate what x to the 10 would have been. So I can utilize that relation to perform the calculation of what the polynomial is without having to do as many multiplications. Now obviously that's not something that's of vital importance for this course, but it is present in the textbook, so I thought I'd mention where the author is actually getting this trick from and why it is useful in practice. Now moving on, let's assume that we're going to just work with our integer hashes now, just to keep things simple. Let's now construct our nodes, and the reason we want to have nodes is, remember I said that when we have collisions, we've decided that we want to treat that by constructing a linked list that is spawned from an entry in the array. Okay, so if we look back over here, instead of having a single value, for example, in the array element 1, I will rather have a pointer to a node. That node itself will contain the key, and then I'll have a pointer to the next one, and so on and so forth. Now again, this is a toy problem in the sense that I'm only storing the keys. In practice, you'd probably want to store something that is associated with the key as well. Perhaps a string, a custom object, or something like that. But for our purposes, we're just storing the key itself. So the important thing to note now is we need to construct these nodes. And luckily, because we've already discussed how to work with linked lists, this is quite straightforward at this point. So what I'm going to do is I'm going to define my node over here, and my node is going to contain two values. It will contain a value, which I'll use to store the key in actually. The notation or the variable name is a little bit undesirable in my opinion, but I don't want to change it at risk of confusing what the textbook is discussing. But just remember that this n underscore value will actually be storing the key, and then n underscore next will point to the next node in our linked list structure. Okay. Now what we have in this data segment here is us simply defining our entire table in memory to start with. Obviously, if you had a more scalable situation, you would not be doing this in a data segment. Again, this is just to illustrate the concept. It shouldn't be seen as a proper industry level version of a hash table. So we have our table, and I'm going to allocate 256 data quads, all of which will have the value 0. Now the reason I'm giving them all the value of 0 is because it's indicative of them all being null pointers. So they're entries in the table that point to no linked list. So it's an empty linked list in some sense. So that's why we're allocating this space as such. Now obviously that's something that often happens with hash tables, is you make a space compromise, so you utilize more space than you would necessarily need to to gain the potential speed benefit by performing hashing as opposed to doing actual lookups or iterative lookups through the entire list. Okay, so now that we have our basic structure, let's discuss how we could implement a function to find a key inside our hash table. So what we will want to do is implement the function find, which will take a single parameter, which will be the key that we're looking for, and I want the function to return a pointer to the corresponding node that has that key in. So just to give that a little bit of context, if I were to
call my find function on my hash table that looks like the one in this figure, say I called find on the value 5, I will go all the way down to this element 7, and then I'll have to traverse this list until I get to this node. And then I want my find function to return a pointer to this node. Okay, and from then the user can decide what he wants to do with it. This way, if we were to extend our node structure to contain some actual meaningful information, they would have a pointer to that node itself. So that's what we want our find function to do. But I've already hinted at how we do this finding. What we first have to do is we would have to hash to figure out what element of this array we need to start looking in. So I perform my hash and I would land up at a specific element. Say I landed up at 7 because I was looking for 5 still. Then in order to try and find 5, I'll have to iteratively look through the list until I find the corresponding key. For simplicity as well in this example, this doesn't cater for the fact that we might have repeated keys or things of that kind. For the moment, we just have a situation where I only have a single key. Okay, we'll implement an insert function just now, which you'll see that doesn't allow us to insert redundant keys. So now we need to implement this function. First thing I'm going to do is I'm going to set up my stack frame and destroy my stack frame. Reason again I'm doing this is because I plan on calling another function. Specifically, I want to call my hash function. This hash function that I'm going to call is the one we discussed earlier with the integer hashing. Specifically, it's just going to mod by the table size. So in this case, it's going to mod by 256 using that nice AND trick we discussed. So on this line over here, I'm going to subtract 16 from RSP because I'm going to utilize a little bit of stack space. Now, again, I'm sticking with the book's notation to avoid confusion. But what's actually being done here is I only need to use one stack space variable in this function, but because I'm actually need to ensure that I preserve alignment, instead of simply subtracting 8, I'm going to subtract 16. The author also doesn't use the EQU op here. He simply dereferences off the stack because we only have one variable. I just want to make that clear that this is the same in this context if I had now said RSP plus .k, for example, and then I had an EQU for k of 0. It would actually be exactly the same thing. So with that set aside, we know we're subtracting some stack space. Specifically, we only need space for one quad word. We'll ignore the extra redundant space. It's just for alignment purposes. Then we're going to save the key that was passed through to us in our function. So the n, in essence, we'll save that onto our stack. So this will be saved in our first stack space variable. And then I'm going to call the hash function. Now remember, if I'm calling a function, the first parameter I have to load is RDI, and the key is already present in RDI. So the hash function will hash what is in RDI, and it will return the result to us back in RAX. Now remember, the result of that hash will actually give us the index where we need to access our array, or our array of entries / pointers. So in order to get back that given element of that array, what we need to do is we need to specify from the table. Now this is from our data segment itself. In this example, we have a static table. It's not like the table is being passed through or anything. This is a table that exists in our data segment. So we start at the label of our table, and then we'll add plus RAX times 8. So RAX will be the index times the data size, which in this case is going to be 8 because we're dealing with data quad words or longs. So all this is doing is I'm accessing the RAX item of table. So say RAX was 10, I'll be accessing the 10th element of this array, which I've called table. So we now get that pointer, and that pointer is now moved into RAX. So RAX will now contain the pointer to the first element of the linked list, if there is anything actually present in that linked list. If that linked list doesn't contain anything, then RAX would actually simply have the value 0 because it would indicate it's actually an empty list. So with that in mind, I'm going to now retrieve my key from my stack space storage and move it into RDI because I want to be comparing against it when I'm searching. Again, I need to retrieve it because I have no guarantee hash didn't change what I had in RDI previously. So I retrieve it from my stack space storage. Then I do a comparison on RAX and check whether or not it is 0. If it is 0, the index, which I've looked up in my table, on this line over here, has returned a null pointer, and that indicates that there is no elements at all that match to that given key or that hash to that entry in that table, which means that there are no nodes to traverse through a linked list. We simply have an empty list, so we can tell immediately that we definitely cannot find that key in our hash table. So with that in mind, if we end up getting a perfect comparison between RAX and 0, we know that we have failed to find what we were looking for, and then we'll jump to the end of the function and simply destroy our stack frame and return. Now, it will be informative to note now that the return value is always the value in RAX, and seeing as we know it is 0, what will be returned back is 0. That's why we can tell over here that if we end up getting p is equal to 0, we know we didn't find it. If I got a null pointer, I knew I was unable to actually find the key I was looking for. If, however, we do get a match, in as far as the linked list is not empty in the corresponding array entry, what we need to do now is we need to traverse through that linked list to see if we can at any point find a match. And as soon as we find the first match, we're going to return that address to the caller of this function. So I'm going to perform a comparison between what is in RDI, which is the key from earlier, to the value of the current node. Now we can make this, offset this again just with inside the struct itself, but we know we can make this successfully because we know that RAX is not the null pointer because we got to this line of code. So we know we can successfully retrieve the current key of the given node that we're searching in. So we check whether or not they're the same. If they are equal, well, we're in luck. We have found the key that we were looking for, and we can jump to the end, destroy our stack frame, and return. Now remember, we'll be returning the pointer that is contained in RAX, and if we got a match, that means RAX will actually be the pointer to the correct node that we wished to return. If we're in a situation that we are not lucky and we do not get a match immediately, what we have to do is we need to iterate to the next element in this linked list. We do this in a very simple manner. We simply set RAX equal to the next attribute of the current node. So we're just traversing one element up. Then we'll do the comparison again. Is RAX 0? Are we at the end of the list? If we're not at the end of the list, we'll jump back up to more and repeat this process again and again until either we find the key we're looking for or we've exhausted the entire list. So now that we've understood or gone through how to find a key, let's try and go through how we can insert a key. What this insert key function is going to do is we're going to have a two-step process in a sense. One, we're first going to check whether or not the key we're trying to insert into our hash table already exists. And if that's the case, we'll rather return the pointer to that node instead of adding a redundant key to the table. And if that key does not exist in the hash table, we'll then add it to the hash table. So that's what we're going to try and do now. So again, we start off with our stack frame setup and destruction, and then we subtract 16 from RSP. The reason we're subtracting 16 in this case is we have two variables we wish to store on the stack. The first of which will be the key that is passed to us. Note it's not mentioned in the slide, but the only parameter that we pass to insert is going to be the key itself. So we want to be able to store that, and we also want to be able to store the hashed value of that key. So we want to have a nice safe storage space for those two values. So first step, we're going to save RDI onto our stack space memory. So we're going to save the key passed to us on the stack, and then we're going to call the find function that we implemented in the previous slide. Now obviously the key that we're looking for is already loaded in RDI. So RDI will do the scanning through the entire table, and it will return to us the pointer that corresponds to where it finds the key if it is already present in the table. We'll then do a comparison between the found or the pointer that find returns and 0. If the returned pointer is in fact equal to 0, that means that that key is not present in the hash table, and we can go ahead and create a new node and insert it into our hash table. If, however, RAX is not null or not 0, we know that that key already exists because we got back a valid pointer. In that case, we'll simply jump to the .found label all the way at the bottom here, destroy our stack frame, and return. And you'll note that RAX at this point, before we perform the jump, will contain the address to the node where we found a corresponding match. So RAX will have the correct value that we wish to return back to the user. If, however, RAX is 0, we now know that we can create the new node. So we're going to now do that. First things first is we're going to retrieve our value or our key from our stack-based storage and move it into RDI. And then we're going to call hash on it. So obviously the first parameter for our function is RDI. So we've loaded RDI with the key. We're going to call hash. Hash will return our answer to us in RAX. We're then going to save the hashed value, or our index in essence, from RAX back onto the stack. Now we're saving it onto the stack because we plan on calling an extra function, and we want to make sure that that hash value is also preserved. We're then going to move node underscore size into RDI to indicate that we want to allocate a node underscore size number of bytes for our new node. So then we're going to call malloc. It's going to allocate that amount of space for us, and it's going to return to us a pointer to our new node. Now the thing that we have to do next is we have to try and insert our newly created node in the correct place in the table, in addition to setting its value to be the key that we wish to insert. So the first thing I'm going to do is I'm going to retrieve the hash value off of the stack. So I'm going to retrieve that by moving it off the stack into R9. So this is our index where we want to insert this into our hash table. I'm then going to get back the pointer or the old pointer in the corresponding array element of the table where we wish to insert. So I think it's easier if I actually indicate this in the diagram. So what I want to do now is I want to retrieve, for example, this pointer over here. Say we had a hashed value of 5. I want to retrieve this pointer and I want to move that into R9 so I can try and change the contents of the list. That is what I'm doing in this line over here. I want to store that value in R8 rather. I want to store that pointer in R8. So what I'm doing is I'm going from my table plus the index that I have retrieved or obtained from my hashing times 8, where 8 is the size of the long. So this is going to return the pointer to the linked list where I wish to insert my newly created node. So now R8 is going to contain that pointer, and then I'm going to change the value that is in RAX is next to equal R8. This is so that my newly created node will point, or its next address will point to the old list that was present in that array element. So that old linked list where we now wish to insert, I want to make sure that my new node points to the start of that list. Then what we want to do is I'm going to retrieve the actual key value from R8, because up until now we've just been working with the hash, but I want to save the key correctly. So then I'm going to retrieve this from the stack and put it into R8. Just because I chose to use R8, I could have used other registers as well. And then I'm going to move that value from R8 into the value member of our struct, of our node struct, specifically the one that we've just created. Now the last thing I have to do is I need to set what the array element points to once we have inserted our new element. So specifically I'm going to set table plus R9 times 8 equal to RAX. So this basically means that I will have constructed my new node. Say for example I constructed this 22, and then I'm going to ensure that this element points to my newly created node. That's what I'm trying to do in that statement. So that's what we managed to achieve there. So now we've linked it up correctly, and now everything is sorted. We can destroy our stack frame and return, and it should also be noted that RAX will still contain the pointer to the newly created node in our hash table. So this is a very simple insert function. Obviously there are more complex ways that we could try and insert a key. However, this is a nice example to get you familiar with working with accessing elements of an array, dereferencing elements of an array, working with pointers that are inside the array and things of that kind of nature. So though the concepts itself are probably relatively simple to you at this point because you've worked with hash tables already, seeing it implemented in assembler gives you a nice practical example of where you can work with all of these different kinds of assembler instructions, where I can dereference, where I can work with pointers, and so on and so forth. Now that we've completed our discussion on hash tables, we can move on to a slightly more interesting data structure, specifically binary trees. Now, a binary tree is obviously a hierarchy of nodes where there, generally speaking, is a root node, and each node will have a left and a right child. What this implies is that the node structure will have, generally speaking, two pointers, a pointer to the left child, a pointer to the right child, and then often it will contain some internal value itself. For our purposes, the node will contain a key, and this key will give us the ability to provide ordering on the nodes. Now, obviously, either or both of the pointers inside the node structure could be null. It's possible that you don't have a left child or a right child. And the binary tree usually imposes an ordering on its nodes. Now, obviously, this ordering is what gives us the ability to perform a binary search on this tree. Why it is termed a binary search tree in this case. We will assume that the keys that are less than the current node's key will be stored down the left branch, and keys that are larger than the current node's key will be stored down the right branch. So this means we'll always have the property that the left child's key will be less than the current node's key, which will also be less than the right child's key. So this is the ordering which we'll always assume present. Now, in a binary tree, just to make it clear, or at least the version of a binary tree we're discussing, we don't have any down-up references. So a child does not have a pointer back up to its parents. We only have this top-down referencing structure. So it's something just to keep in mind. Just for simplicity as well, in this example, we will not store duplicate keys. Obviously, if you look through the functions we'll discuss, it's actually quite trivial to extend it to work with duplicate keys, but I think it's best if we keep things simple for the moment. Now, we need to define our structure for our node. So we will have three attributes to our node structure. Specifically, we'll have the left child pointer, the right child pointer, and then the key that we wish to store in that node. We will refer to that key as the n_value just to stay in line with the book's notation. So this is our node structure that we're going to work with. Again, we don't have to worry about any alignment concerns because they're all data quads and we end up having perfect alignment as a result. In some sense, we got a little lucky. If, for example, our value was not a data quad and say a double data word, we would have to add a little bit of alignment to make sure everything works correctly if we were to port this to C and C++. Now, the question that we have to answer is, how do we want to represent our tree as a whole? Now, the first or the easiest option in some way is to simply have a pointer to the root node. This sounds appealing, and it's how we actually implemented our linked list. However, it has the obvious downside that if at any point I perform an operation on my tree where the root node would get changed, then whoever is using this tree object would need to be informed of that change. So it adds an unfortunate side effect in that way. So we're going to make things a little bit nicer and rather actually implement a tree structure itself. Now, this tree structure will contain a pointer to the root node. So this means that the people that are using the tree will have the tree structure and they don't have to worry about whether or not their root node pointer is updated or not, because we'll have to handle that ourselves. So you don't have to inform everyone that a change has been made. It makes things easier all around, really. We're also, for the sake of nicety, we're also going to add another little property to our tree structure. We're going to add a count value. This is just to count the number of nodes that are present in our tree. So our structure for our tree is as follows. We'll call it tree, and we'll have a count to indicate the number of nodes, and root, which will contain a pointer to the root node. To implement our new tree function, this is just to allocate a new tree to work from. What we'll need to do is first set up and destroy our stack frame. That's because we plan on calling at least one extra function. What we will now do is we'll move the size of the tree into RDI and call malloc, so we'll allocate a contiguous chunk of memory. In this case, it will be 16 bytes. And then we want to specify the root node of our tree in addition to the number of nodes present. However, at the moment, the root node should be null because we don't actually have any elements in our tree. And in the same sense, we obviously have no nodes, so the count should also be 0. So that's why we XORed EDI, and then we move that 0 value into both the root to indicate it's a null pointer and 0 into count to indicate that there is no nodes present. Now that we've gotten the basic structure, let's think of how we could implement a find function. Say we have filled in our tree over time and we want to now find a specific key inside our tree. So obviously you could do this in a somewhat blind fashion. However, we're going to rely on the fact that we have ordering on our tree. That was how we designed. So we're going to perform a binary search on our tree. The tree or the find function will take two parameters. We'll take a pointer to the tree itself and then the key that we are looking for in the tree. Then we want to return the pointer to the node in the tree where we found a corresponding matching key. So we start by setting up our stack frame. In this function, we don't need to worry about any stack-based storage, so that's easier for us to handle at least. We're then going to move the root value, or the root member variable in some sense, from the tree structure into RDI. So now RDI will actually contain the pointer to the root. So we've deferred from the fact that we're working with the tree to now working specifically with the root node of the tree. Then we're going to zero out RAX. And the reason we're zeroing out RAX is that I want to use RAX to be my return value, and I want to have it to have a default value of 0. Specifically, if I fail to find a node in my tree, I want to return a null pointer. So I achieve this by having EAX or RAX in our case actually have the value of 0 to indicate that it was not found. Then I'm going to compare RDI with 0. Now, if RDI, which is our root node, is in fact equal to 0, it means we already have no elements in our tree. And if that's the case, we can simply jump to done, destroy our stack frame, and return. And we will return with the knowledge that RAX has the value of 0. So whoever has called this function will get back a null pointer, and I'll know, okay, well, I was unable to find the key I was looking for in that tree. If we're in a situation where our tree actually has a little bit more substance and it's not just an empty tree, we should pass this first jump, and then we can start comparing actual values to the key. So I'm going to compare RSI, which, if you recall, is the second parameter that is passed through in a function, to the value attribute of my current node. So I'm comparing this n from RSI to the current value in the current node, or the value in the current node, rather. If RSI is in fact less than the current value in the node, it means that I should be looking down the left path of the tree. So that's what I'm doing in this jump here, that I end up having a less comparison, so RSI is less than this value. I will go left. So I'll jump to this go left label. And this is representative of me moving down the left path of the tree. Once I'm moving down the left path of the tree, to achieve this, I just have to update the pointer of the current node I'm in. So I simply have to set RDI to be the left child of my current node. So I've just moved one branch down to the left child. Once I've done that move, I can jump back up to the more label and I can repeat this comparison approach. If I'm in a situation where RSI is in fact greater than the value in the node, then I know I should be looking down the right path of the tree. And I do that by jumping to go right, and I perform the same kind of operations as I did when I jumped to go left. So then I will move the right child's address into RDI. So I've moved down the branch in the rightward direction. Then I'll jump back up to more and I'll repeat this process again. If I'm in a situation where I make the comparison and neither of these two jumps trigger, it means that RSI is not less than or greater than the value of the current node, which means it must be equal. So that means we've found what we're looking for. And all we have to do once we've found what we're looking for is return the address of the current node. So I'm going to move RDI, which contains the address of the current node, into RAX, and then jump to done. Destroy our stack frame and return back to the user. And the user will get back the pointer to the node that has the corresponding key they were looking for. If I'm in a situation where I keep branching left and right and so on until I'm at a point where I actually have hit the end of the tree or the bottom of one of the paths, I'll be in a position where RDI will in fact equal 0, which means I've hit a null. And now the first time I hit a null, it means that I'm certain that that key does not exist in that tree because the tree has the ordering imposed on it based on how we've designed the keys, such that the left child is always less than the current or the parent, and the parent is always less than the right child. So if we ever hit a null, we know that we've exhausted the search and we cannot find that key. So if we hit the null at any point, we know, well, that item we're looking for, that key we're looking for, is not in the tree, so we're simply going to jump back to done and return, relying on the fact that RAX has the default value of 0. Something that I just think I should mention, in the textbook, this RDI over here is in fact an RASI. That is a typo that is present in the book. I think it is in both the first edition and the second edition. I'm not sure about the third edition of the book. Now, if that RDI was an RSI, what would happen is you would actually simply return the key that you were looking for if a match happened. So if that was a 5 and you found a 5, this would make sure that you ended up returning the value of 5, which is clearly not what you were intending to do. You wanted to return the pointer to the actual node in that tree. So that's why that should be an RDI. We can now move on to the slightly more challenging task of inserting an item into our binary tree. So let's first go over an overview of our strategy to do this insertion. I feel it's important to have a slight overview because the code for this function is slightly longer than the ones we've become accustomed to. So the first thing we want to do is we want to check if the key is already present in the tree. Now remember, we said earlier that we've decided that this tree will have no repeated elements. So we're going to first check whether the key is in the tree. And if it is in the tree, we can simply return back the pointer to its node. If the key is not in the tree, what we will do is we'll create our new node. We'll set its value to the given key, and then we'll set its two children to null. The reason we know we can set the two children of null is because when we insert into the tree, we will move down the tree based on the key values until we find the appropriate place to fit it, and we'll attach it at the base of a tree or onto a leaf node of the tree. Now, there's a special case we also have to deal with, and that is if we have an empty tree. Now, the only thing that's a little bit different is that if we have an empty tree, we have to set the root attribute of our tree object to point to our newly created item. It's the only thing we have to do in the special case. If the tree is not empty, then we have to traverse down the tree, going sometimes left and sometimes right, based on the found key in the node that we're currently in, until we find the correct place to insert our newly created node. So that's a general overview of what we're trying to achieve with this insert function. So to start us off, our insert function will take two parameters. It will take the pointer to the tree and the key that we are looking for. It will also then return the pointer of the location or of the newly created node in our tree. So that's what we want to achieve. We will have two variables which we will be storing on our stack. Specifically, we're going to store the key itself and the tree. We want to have a nice safe space to store those two. We're going to set up our stack frame, subtract 16 from RSP, so we have space for both of our two variables. Then we will save them onto the stack directly. I'll save the first parameter, which is the pointer to the tree, onto the stack, and then I'll save the key value itself onto the stack as well. Then I'm going to call the find function. Remember, the find function has the same prototype as this insert. Specifically, I'll take the tree and the key that we're looking for. So I know that those are already preloaded for us, so I can call find. Now find will then return to us the pointer of the node, which has a matching key if a matching key exists within that tree. So with that in mind, I'll then compare the returned pointer of find to 0, which will obviously, the return pointer will be in RAX. If that return pointer is 0 or null, we know that that key does not exist in the tree, so we can proceed to create our new node. If, however, RAX returns a non-zero value, so it's an actual valid pointer, we will end up in a situation where we will jump based on this, so jump not equal to the done command. So this will basically jump us straight to the end of this function and will directly return, relying on the fact that the pointer to our node is already in RAX. So let's assume for the moment that the key is not present in the tree. So that means we will go past this jump statement and move on to the creation of our node. So we'll first allocate the space for our node. So we move the size of the node into RDI, then call malloc. So we've allocated our contiguous space. Then I will load the value that I want to store inside this node into RSI. So I'm going to retrieve that back from the stack. Then I'm going to move that value in RSI into the actual structure member variable value. Okay, obviously I'm using the offset notation that we've become familiar with by now. Then I want to set the left child and the right child to both be null pointers. I do this by XORing RDI, so RDI will have the value of 0 after this line. I'll then move 0 into both of these two member variables. So the left and the right nodes, or the left and the right pointers, will both point to null. So we've done our first two steps of our overview so far. Moving on, we now need to cater for the case where we have a tree that actually has no nodes present. And this is where we need to try and assign the newly created node as the root. So what we are going to do is we're going to first retrieve the tree from our stack-based storage. I'm going to move this into RDX, and then I'm going to extract from that the count, so the number of nodes present in that tree itself. Now RDI will contain that count. I'm then going to compare RDI with 0. If RDI is equal to 0, it implies that our tree has no nodes, and we need to deal with the special case. So assuming RDI is in fact 0, we will obviously not jump because they are equal, and we'll implement these next three lines. So first thing I'm going to do is I'm going to increment the count that is in my tree. Just as a little bit of a reminder, you'll see that I'm using this Q word over here with this increment statement, and that is because there is no way for the compiler to deduce the size of this count given what it sees here. That's why I have to tell it that this count is in fact a quad word. This is an extra reminder of why I'm using this quad word. So now I've incremented the count by 1 to indicate that now my tree will actually contain one item, specifically my newly created node. Then I'm going to move the value that is in RAX. Remember, RAX is the pointer to my newly created node from the previous slide. I'm going to move that into the root member variable of my tree. Once that's been completed, I'm going to jump to the end of the function and return, and obviously everything will work out fine because RAX will contain the pointer to our newly created node as we desired. The next thing we need to do is the more complicated part, and that is to actually insert a node into our tree, assuming that the tree actually contains nodes already. So what we need to achieve, in essence, is we need to be iterating through our tree in an intelligent fashion, specifically relying on the fact that there's an ordering to find the correct place where we can actually insert our newly created node. So first thing we're going to do is we will be executing this, or executing from this find parent label. That's because we would be in a situation where RDI was greater than 0. So we will jump not equal to find parent. So we need to execute from this label. I'm then going to increment the count of my tree to indicate that I'm adding a new node. Just as a quick mention, it is possible to avoid repeating this increment by rearranging things slightly, but I don't want to deviate too much from the book. I don't want to add unnecessary confusion. So we increment to indicate that we have a new node. Then I'm going to move the root of the tree into RDX. So now RDX will be the node which is the root of our tree. And we can now follow a somewhat similar procedure to our find method to try and actually locate where we can insert into the tree. So the first thing I'm going to do is I'm going to compare the value that is in my current node, so in this case it will actually be the value in our root node, with what I have in RSI. And if you recall from the previous slide, a little further back, RSI will still contain the key that we are looking for. Now, based on that comparison, we can decide whether we need to move down the left path of the tree or down the right path of the tree. If RSI is in fact less than the value of the current tree, the value that is in the key of the current tree, we know we need to traverse down the left side of the tree. In that case, we're going to jump to go left. So now we'll execute from this label. We'll then move RDX, which is going to be the pointer of our current node that we're looking into R8. We'll then set RDX to be the left child of that current node. So now RDX has moved down to the left child. We then compare whether or not RDX is in fact null, whether or not we've hit the end of our tree. If it is null, that's great. We've found where we can actually insert into the tree. So let's assume it's null for the moment. Then this jump will not happen because RDX is equal to 0. And then all we have to do is move RAX, which will contain the pointer to our newly created node, into the left member variable of the current node that we are looking into. So we've basically fitted it in the left child of a node that is present in the tree, where that current node didn't actually have a new or any left child. So we found an open space to insert our new item. If, however, we are in a situation where we see, okay, well, we're not at the point where we're at the end of the tree and RDX is not equal to 0, we then jump back up to this repeat find label, and now we have to continue our search to find where to insert. So we again compare RSI with what is the new current node and what its value is, and based on that we'll decide whether we need to jump left again. If we're in a situation where RSI is in fact greater than the value of the current node, we are in essence jumping right when we execute, or moving right rather, when we execute these lines over here. We just don't need an extra label for it. And then what I'll do is I'll move RDX again into R8, then I'll set R8 to be the right child, set RDX to be the right child of what is in R8. So basically I'm moving down the right branch again. Then I'll check whether or not RDX is in fact null. Have I hit the end of the tree? If I have, I can insert my new node into the right child of my current node, and then I can return by jumping to done. If, however, I am in a situation where the comparison here tells me that RDX is not in fact null, I have to jump back up to repeat. So I'll continue this process again and again and again until I hit a null. So I'm moving left, moving right, and so forth until I end up at the point where I hit a null, and that means I found the correct place where I can insert into my tree. Again, you need to remember the fact that this is all relying on the fact that this tree has an ordering property based on the way we've inserted into the tree. Specifically, that the left child will always have a key less than that of the current node or the parent node, which will also always be less than the key value of the right child. Okay, so with this in mind, we now have figured out how to insert into a tree. Now, I think it would be a good exercise for you to try and figure out how we would delete a node from a tree. Now, it's not the most straightforward function, obviously in assembler at least. In C++ it's very straightforward, but in assembler you have to jump through a couple of extra hoops. So it's a nice example to try and ensure that you understand how this insert function works. You can implement the delete function yourself. The last function which we'll discuss now is a print function, which we have designed to print out all of the items, or all of the keys rather, in our tree in order of lowest key to highest key. The way in which we do this is we will first construct a non-recursive function, which we'll call a recursive function. The only reason we have to have this two-layer approach is because we have our tree object distinct from our nodes inside our tree. So we'll have a function called print. Print will take one parameter. Specifically, that parameter will be a pointer to a tree structure. So we'll start again by our standard stack frame setup, and then I'll extract the root node from my tree. So the root node will now be stored in RDI. I will then call my recursive print function, which we'll get to shortly, to print out the sequence of items in my tree. And once we have done that, I want to then print out simply a new line character. So for the new line, it's straightforward. We have our data segment. I have a little print format here, which is just indicative of a new line character being output. I'm going to load the address of this print label, XOR EAX, to indicate that there are no floating point parameters, and then call printf, which means we'll just add the new line. Then I will obviously destroy my stack frame and return. Now the meat of this function obviously is this recursive print, which we'll go through now. Just want to mention something quickly. This XORing of RAX is not present in the textbook. I think again it's something that's just been accidentally omitted. Just bring your attention to the fact that that should actually be present. Moving on to the recursive function itself, again, we start with a stack frame setup and destruction. Obviously, we know we're going to call another function, specifically the recursive print function in our recursive function again. So stack frame setup and destruction is quite vital, actually, in this case. We then also want to reserve some stack space because we want to save something on our stack in a nice save function across function calls. Now, we only need one thing specifically on the stack for this function. However, again, for stack alignment, instead of just reserving 8 bits, we reserve 16, so everything stays on a multiple of 16 boundary. You will note something that is a little bit confusing, but I didn't want to deviate again too far from the textbook. You will see that this is a t that is passed through to the function. However, this t is actually a node. It is not a fully fledged tree. What this means is that this t will have the three parameters we've been dealing with, or the three member variables we've been dealing with, specifically a value, a left child, and a right child. I just want to make that clear because I think it is quite confusing to reuse the notation t. But nonetheless, now that we know that t is actually indicative of a node itself in our tree, we can continue. First thing I'm going to do is I'm going to compare RDI with 0. So I'm checking whether or not I'm actually at the point where I'm at a null in my tree. So this means I've hit the end of the path that I've been traversing. And if that's the case, I'm simply going to jump to done over here and then destroy my stack frame and return. You can see this as your base case in your recursive function. If I'm in a situation where they are not equal, now I need to actually start printing out the rest of the nodes. The way I do this is quite straightforward. I'm first going to load RDI onto the stack. This is because I want to make a nice saved copy of my current node, because I'm going to call a function and I want to still have access to my current node. Then I'm going to set RDI equal to its left child. So now RDI will actually be pointed to the left child of the node that I originally started with. Then I'm going to call recursive print. Now recursive print will see the left child as the new start of its tree in a sense, and it can perform the exact same operation again. So when we call this, you can see it as printing the left subtree. That's what we're doing there. The next thing we're going to do is I'm going to then print the actual value of the node that I am in. That's obviously because we know that everything that this recursive print over here would print will actually be less than what we will be printing when we print the value of my current node. So I'm going to retrieve the pointer to my current node from my stack and move it into RDI, from which I'm then going to extract its current value and move that into RSI. I'm then going to load the print format, which is just to output a long and a space, into RDI, set RAX to be 0 because I have no floating point parameters, and then call printf. So all this is doing is I'm printing out the long that corresponds to the current node that I'm in. Again, the textbook for some reason does not have this XOR statement. It should be present. So we've now printed out the current item, and what we need to now do is we now need to print out our right subtree. To do this, we retrieve the pointer to our initial current node again from the stack, move it into RDI. From there, we set RDI to be the right child of that node. So we do that again by accessing the member variable n_right. We set that to RDI. We then call recursive print, and that will print the right subtree. Now, if the way this is working is a little unclear to you, I recommend maybe have a quick look at some recursion examples again with trees, just to recap on that side if that is where your confusion is coming from. However, this is very much standard to the way in which you would do something like this in C or C++, or the logic behind this is very much straightforward. You just have to get used to the assembler way of accessing the internal variables. So that brings us to the end